The original work that was done to kind of get an idea of what was going on in these reservoirs in terms of layered no cross-flow reservoir behavior turned out to be a gas field in the West Panhandle, the Red Cave. It's a sandstone reservoir, about 1,800 feet deep, and there was a consultant working on the problem because there was a major problem in this whole area where the oil operators were going in and perforating in our gas cap. The ownership out there was one operator can own the oil and another operator can own the gas. And that created a real serious problem because some operators were going in there and perforating the gas cap and putting refrigeration units on it to recover liquids and calling it oil wells. And they were stealing our gas, and then they had, once you had it classified as an oil well, you could drill on 40 acres. So they can put how much is 40 into 640? 8 wells on a section, and we were only allowed 1 gas well. They were just draining the hell out of everybody else. And that's what this was all about. We were trying to stop it first in the Red Cave because they were doing the same thing here, and then they were doing it throughout the entire Panhandle because this was a gas cap over an oil rim, and the gas in there was rich enough to recover quite a bit of liquids. So the consultant said, why don't you take a look at the Ratetime data on this field? It's obviously exponential. So we got into Dwight's and we start looking at the Ratetime data. Let me give you a little bit of a background on the field first. Your first production was in 1961. Your full development, over 212 wells on 640 acre spacing. All the wells were drilled up in 1966. The depth about 1,800 feet. The gross thickness, 350 feet. It's a nice thick reservoir, a sandstone. Reservoir temperature 80 degrees Fahrenheit, initial pressure 428, porosity 15%, water saturation about 50%, the gas gravity 7/10. After it was all developed, you can go back and you can correlate about a 50-foot thick shale across the whole field, east to west and north to south. At the time, that didn't necessarily mean very much to us, but the average well, original gas in place was about 1.5 billion, and all the wells were originally stimulated with sand fracs. So we started to take a look at the individual well Ratetime performance. And this is a typical example of a good well and a poor well, a semi-log plot rate versus time, and as you can see, you had this early rapid decay. When we looked at this, because we just knew this was a low permeability stimulated reservoir. Nobody had ever really measured or published or did any work to evaluate the permeabilities in the first place. So we thought, well, let's go ahead and reinitialize. We'll look at this, and if we reinitialize somewhere through there, that we'll be able to get the B value into pseudo-steady state. That's what we were thinking at the time. You can see again here, let me make a couple real important points. The effective decline rate over the first year, that's the Q at Q1 minus Q2 divided by Q1, expressed as a percentage decline, okay, over a 1-year period. The effective decline over the first year was 42%. Last year in through here was 7%. Well, it's interesting, and theoretically, if you look at the equations, whether it was a good well or a bad well, the percentage decline first and last year are always the same. And this is a characteristic of layered no cross-flow reservoir behavior. A big change in the effective decline as compared to early time and late time. Okay, you're going to get copies of some of these papers and look at some on water floods where they said, well, initial decline was 25% and the current was 7 or 10. and it's obvious that we had to do water flooding. Well, they didn't realize what that was trying to tell them. That you have a high B value, okay? A B value of 0, you have the same decline at the beginning as at the end. It's a constant. The higher the percentage change, the higher the B value. So look at this sometime in some of the papers, because they'll start off justifying this is why we had to do a water flood, because we had a rapid decline. Not only in rate, but in pressure. And think about it in another way. A lot of people attribute rapid decline in pressure as a highly undersaturated reservoir. You'll see exactly the same phenomena, even if it's saturated, okay? That you might attribute to being only a result of being highly undersaturated. Read a lot of the old papers and look at the behavior, and invariably that's what was always said. Again, it's layered no crossflow reservoir behavior. When we took the data, and this is these same two wells, and plotted it log, lo and behold, it becomes real clear. I hope you remember how the type curve looked. If there was any transient data, there should have been a stem coming up like this and then coming down. Every bit of that data fits a B value of 0.9. The semilog looks like transient, but it's not. It's a high B value. So that's another characteristic of layered no crossflow reservoirs, a high B value. And I'll show you later, again, I like to reinforce some of these things. The higher the B value, the more the oil or gas is in the low perm layer. The bigger potential is to go after something. So we took, well, let me get the other one first. We looked at all the wells, and all the wells that have any data at all in terms of rate time. You can only put so many on a plot. Well, this is 10 wells. We used Mylar and different, we learned some techniques as a result of doing this. We used the Mylar in different colors and different symbols. These are 10 different wells, and they all overlay each other. They're all shifted by the coordinates, the dimensionless rate and dimensionless time, okay? What turns out that the B value for the total field is 0.9. Okay, now another rule. If I have a B value of 0.9 for the total field, I don't know whether it's layering or regional, okay? So I look at the individual wells. If the wells have a B value very close to the total field, then it's layering. There's no question. It's a layering effect then. So again, diagnostic tool, a rate time analysis to be able to determine reservoir, a description, layered no crossflow. It is not regional. What turns out that okay, I'll get to that later. When I was in the gas department, we had a separate department where gas reservoir engineers were in the department. We ran isochronal tests. As the wells were originally completed, we ran isochronal tests on every gas well. But we primarily used the isochronal tests for performance monitoring of the wells, where we'd plot the curve, and then maybe annually or every time you can get a shut-in and a flow on the well, you take that data and you plot it on a back pressure curve to see if there was any deterioration. We never really did any analysis of that data for permeability and skin. Well, we took the original data and used the type curve approach and superposition and everything else. And these are the same 10 wells you saw the rate time on, the thicknesses with regard to the pace on those wells, averaging maybe about 50, 60 feet. The total well permeability averaging, well, average 46. The total permeability averaging around 20. The skins, we go back about -4.5. We did good jobs with regard to the stimulation on the wells. It turns out when you finally end up doing all the analysis to make everything to come out whole, particularly get a B value of 0.9, You need a permeability contrast. We're assuming the skins are the same for all wells. You need a permeability contrast about 10 to 1. And a thickness contrast of 1 to 2, where you have twice as much in the low perm layer as you do in the high perm layer. So there's a lot more to go after there. I don't remember whether they did individual stimulation at the completion of those wells or not. But when you split it up into 10 to 1, now you see why there wasn't any transients. You know, the high perm layer is averaging around 50 millidarcies. Yes, always remember, during the transient testing of any well, there's no possible way you can determine a reservoir is layered no crossflow or if it has crossflow, because the transient period acts identically the same, exactly the same. One of the layers has to go into depletion before you could ever see any difference between a crossflow and a no crossflow situation. So you can't determine it from transient testing. All you get is the total KH, and that's what this is. That's the total, but these are the individual layer Ks. You know, they're substantially different. You know, this is 5, and that's about 52. And again, that's why you see no transient performance in the early rate time data on these wells. So things started kind of making sense. The way we approached the problem, again, we used these very simple equations. What is no crossflow? Well, it's the sum of two you separate rate time you forecast on a well. The flowing pressure is common to both, so they're totally independent of each other. You know, this is a constant wellbore pressure situation. If it was constant rate, they're competing with each other for the total flow, but that's a different situation. You know, that's why we were lucky in two ways to get involved in this problem to understand what's going on. The field came on virtually wide open from the beginning at about a 50-pound line pressure, you know, real close to the 10% that we need for a B value, a 0.4. To where we had all of the rate time data available on these wells. We were able to do the analysis. Now the only way, it turns out when, you know, for flowing pressure 0 or a back pressure curve slope of 1, which is what should be expected for this range, the exponent ends up, a B value of 0.5 is a squared term. Now the only way that I can end up for with a sum of two separate forecasts with B values of 0.5, to be a 0.5 is if I have a common denominator in these two terms. In other words, the Q max over G sub I, the more permeable layer, we're always going to refer the subscript 1 to the more permeable layer, and the Q max over the G sub I of the less permeable layer, if they're the same, I have a common denominator them and have a B value the same as each individually. Okay, with a further part they get to, I'm going to be adding two values of 0.5, and I'm going to in this case end up with a 0.9. There's a set of tables in your notes for this is the gas solution. So we took the single phase liquid solution and we did the same thing where each layer would have a B of 0. And we combined them. You present them in a table, Q max over G sub I as a function of the volumes of the layers. And you can get as high as 0.6 or 0.7, each layer individually having an exponential decline. So we didn't get the high value of B of 0.9 because we're adding 2.4s or 2.5s together. Okay? You sort of get that in your head. But using these two real simple equations, we were able to duplicate the rate time decline with a B value of 0.9. And we finally started understanding what was going on. And you didn't have to get complicated. And again, you're dealing with a volume ratio and a Q max over G sub I ratio. In a Q max over G sub I ratio, again, this is nothing more than the absolute open flow over the gas in place. And this is, again, for simplicity, this is one well. When we ended up doing the model study on the Oklahoma Hugoton, we were able to use these equations to do some analysis in terms of the G sub I would be the gas in place for a given layer. It was a 12-section model. And the Qmax would be the sum of the individual pseudo-steady state curves, okay? The Winfield layer had originally completed only 3 wells. The Harrington had 12, and the Kreider had 12. So what we ended up doing was the pressures that we measured in the expendable well, the Kreider and the Winfield were about equal. So for that to happen, we knew that the ratio of the Qmax over G sub I, those 2 layers, had to be about equal. Okay, a very simple concept, how I can get there real quick in arriving there. The other thing, keep in mind, I'm going to point out early, because I'd like to repeat it over and over, the people who do reservoir simulation are going to, they deal in terms of K over phi, okay? It's the same type of concept. When you plug in reservoir variables, you say, well, I can reduce that to K over phi. Well, the Q is got some other parameters in it. It's got skin, and it's got the pressure level. Okay, so you can have a different pressure level. It's going to a different Qmax. Where the volume ratio really surprised us when we did the Oklahoma study is the volume ratio is always fixed. Okay, from the standpoint of phi h over phi h. All right. What ended up happening in the Oklahoma Hugoton is the field produced at a constant rate for about 45 years. Originally, the volume ratio in terms of gas in place was 2 to 1 originally. So if we'd have turned it on, the field on wide open at the beginning, we'd have got a predicted B value of about 0.6, okay? But by the time it went on depletion, the volume ratio switched. The gas in places now were 1 to 2. And the B value you should expect when it started on decline ends up being about 1. So you can't deal in terms of just reservoir variables, okay? The pressure level, particularly in gas, becomes very important. And this was a big surprise, because I'd always thought that the B value for a field, once it's established, is always fixed. Well, when you get into layered reservoir, now we're running into some additional concepts. That it's better to look at this in terms of gas in place, because then the pressure level enters into the problem. I'll show you later, towards the end, how we took the model. Once we had it matched, what if we produced it from the beginning? And we saw a B value about 0.6. And then we were able to compare that to the decline exponent when it was going to go on decline within the next year. And we got 2 different values. We discovered something that we would have never found out if we hadn't played this little game with the model. It was a big surprise. This shows you really what we're ending up doing. This is the rate time of the low permeability layer, right down here. This is the rate time of the high permeability layer. And if you add this one to this one, you get this one. That's all it is. So you have the 2 very simple equations. And we're going to work an example yet tomorrow on gas, and we're going to do exactly this individually. So when I add this to this, I end up with this, and that just about fits the B value here of 0.9. And this is for the red cave, so that's how we were able to get there. Well, then you can take a look at skin. Because originally you were just talking about permeability ratio. Well, that's not really right, because I can actually end up having equal permeabilities, but I can have different skins, and I can still end up with the same ratio. So all this is here is if I have a +5 on a more permeable layer and a 0 on the less permeable layer, or a 0 on a more permeable and the -3 on the less permeable, when I put it in terms of Qmax over G sub I, the numbers come out the same, even though the permeabilities would be different. As long as these numbers are the same, the data is going to exactly overlay each other. This is for the one set of data is for a +5 skin and a 0 here, and the other set of data is also for a 0 and a -3. So it's the Qmax over G sub I. You can't depend only on the permeability ratio, okay? You got to introduce the concept of skin in the problem. And everybody is involved in reservoir description, reservoir characterization. Just read their papers. They don't even recognize the idea, or that skin is a very important variable into the problem. Also the pressure level. Each one of these by itself, this has a B value of 0.4 and this has a B value of 0.4. And that's how you end up getting a composite. You get a higher B value. You know, and you can see, look, way out here at the end, it's hanging in for a long time. What would this be? Maybe 30 years, maybe even 40 years. It's hanging on a B of 0.9. Well, long time it's going to start dropping off, because if you were to use a real high B value all the way, you're going to get way too larger reserves. But you know, out in here, you're in a region of about 100 years almost, at least out in here. But you keep that in mind. You can't use in fact, after working out the problem by hand, I'm going to tell you, be very careful. Don't ever use a forecasting B probably higher than about 0.8, you know, for layered no cross-flow reservoir. Because when you run into 1, you approach dividing by 0, and you get into real trouble, and you have infinite reserves that way. So you could use as a diagnostic tool. I'm going to tell you, if you can get a B value in a range of 0.9 or 1, I'm going to tell you the volume ratio is probably twice as much in the less permeable layer than in the more permeable layer. And that starts to give you an idea how much is there to go after. I'll show you when we get to the P over Z. You can exactly demonstrate the ratio of the pore volume by the P over Z plot. This is a P over Z plot. We generated this with a model to try and understand what's going on. P over Z versus cum, but remember, this is total cumulative production. This is the gas from both layers, and no one has a meter downhole to measure each one individually. Okay. That if you were to measure each well or each layer by itself, its pressure plus its cum, it'd be a straight line. What we're seeing, though, is we're getting a pressure that is a bastardized pressure in between, and we're getting a total cumulative production. So you end up, you can get these types of P over Z curves. This is nothing more than if the ratio of Q max over G sub I is 1, even though there's no cross flow at all occurring, okay, they're both going to deplete equally. So you're going to have the same pressure in each layer. So you can still have no cross flow, but it isn't going to make any difference. And this is why you're obligated as a reservoir engineer, as far as I'm concerned, you say, yeah, but I don't know if the shales are continuous. You must run that case. And you might be lucky that by the time you plug in all the reservoir variables, it's not going to make any difference because the ratio is going to be 1, okay? So it might not drastically impair your production forecast. I'm also going to tell you that the work we did on the Oklahoma Hugoton is if you just took the core data, there's no contrast. But when you take the pressure transient data, there's a contrast of 10 to 1. You have the core data, there was an order of magnitude difference in the permeability of the crider between what you would describe from a core description and what we were able to describe from a pressure transient in combination with core. What we ended up doing, the Harrington is the low perm layer. We described it with the phi K, okay? And then we had pressure transient. We had a isochronal test or multi-point tests on every well, and we got a total KH. These wells that were completed in only the 2 layers, the Harrington and the crider. So we got the KH from your phi K relationship for the Harrington from the core data, and subtracted that from the total from the well test, and that was the KH we used then for the crider. And every time I make this kind of presentation, somebody says, but that's arbitrary. No. The only way you can match the layer pressure that we measured is to have the contrast that we got by using this procedure. If you would have used the KH from the core for both, you would have never been able to get the contrast between the 300 pounds in the Harrington and 100 pounds in the Kreider. You have to have the contrast. So it isn't arbitrary. And again, this is just understanding the logic that you're working with these very simple concepts. The volume ratio here is 1 to 1, and all that's saying, well, the high perm gas in place is 0.75. Okay, right here. The total is 1.5. So you can look at that early P over Z and say, well, that's approximately asymptotic. If I take that data, it's trying to extrapolate to the gas in place of the more permeable layer, approximately, okay? One of the characteristics that you saw in the example in a red cave is the curvature indicating it's a possible layered no cross-flow reservoir. There's a copy of a paper in there of some people who did, it's not infill drilling, in fact it's exactly a sidetracking of 18 wells in the San Juan Basin, over 1,000 feet thick, and they increased production by a factor of 10. It was sidetracked. By going in there and individually, after they did that, then they individually stimulated each of the layers. The way he knew that there was a problem, you can end up with a big contrast such that you can still get a straight line, and all it is trying to indicate is the gas in place in a more permeable layer. So this could be an indication. Why? Because my volumetric estimate is 1.5 and I'm only seeing 0.75. Okay, another indication layered no cross-flow reservoir behavior when your performance, the history match of this would be perfect, with the pressure data, but a big discrepancy between volumetric. We used to blame geologists. I used to. I don't anymore. That those numbers by good geologists doing reasonable work, if they're very much different than what the material balance is giving me, is saying I have layered no cross-flow reservoir behavior, and this is the situation on Eta. There's a big difference between what was mapped originally by good geologists in different companies on the total oil in place there as compared to what we're getting from material balance. And then when you get recovery factors of 35%, it's absurd, for this type of reservoir. And the pressure level, go ahead and run any water influx type of problem with low permeability, and you see you can't get water in there. But there's a little different. If it's intensely naturally fractured, then you're not dealing with an average permeability of 1. The fracture storage wall, or the fracture itself, could be tens of Darcy's, and that could result in water influx. But the fact you have water in a well bore may be producing, but every well produces some water, so that doesn't necessarily justify the conclusion of water. But you've got to examine every aspect of the problem. Okay, see how close you can get to match by running ETA in 2 separate 3240s. Because you have another history matching parameter in there, and that's you're assuming full water drive whenever the gas-oil ratio is going down like it is. You get the same type behavior with a layered no cross-flow for solution gas drive. You're getting the initial gas-oil ratio, the more permeable layer, and then later you're getting the low. And if it's highly undersaturated and it's producing low rates, you'll stay undersaturated forever. Okay, so the gas-oil ratio will go up and then it'll come down. It'll stay down. So that's another matching criteria that you have for all reservoirs that you don't have in gas. But keep in mind, the possibility if it's straight, you say, well, that's not layered no cross-flow. Well, it could still be that. It's just you got a lot of low permeability, really low permeability stuff that you might go after. And the San Juan Basin paper, what you really have to appreciate there, particularly since we've been involved in infill drilling, instead of sidetracking those wells just 100 feet away, had they drilled them in the middle of the section, what would everybody have concluded? Aerial variation in reservoir properties. Bullshit, okay? This is why I'm coming down so strong on this particular aspect. When you really understand what's going on and you look at lots of data, there is not a single case that they can document in the literature to prove this aerial variation is important. The real problem is vertical. you know, take the situation which has actually occurred in some, you go from 40 acres to 20 acres to 10 acres to 5 acres, and every time you drill you get an increase. Impossible. Okay, it's illogical that I can have that much variation aerially, that I'm always getting these increases. You're going to give you an example problem. It's a little long, but it's one that I hope that we can get through. I'll show you how we can produce a rate time on a liquid solution with infill drilling, but what you're really doing is you're drilling them in a low perm layer with these big spikes of increasing in apparent increasing in production that other people would interpret as being, well, in fact the papers interpret as being aerial variation. The example you'll work, it's exactly the same permeability horizontal. You're assuming it's constant in each layer, and you're just doing the drilling. You'll see the exact same spikes, the exact same increases. You know, where the rate's even higher than the original. But this, the two little green dots on here were kind of to give you an idea of where we were in the Oklahoma Hugoton, like when the pressure in the more permeable layer was around 110, 120. You had less permeable layer, it'd be as high as here is around 380 pounds. And anybody, if you don't understand the concept, you say, well, this is what really kicked everything off. Some of the independents were going out there and drilling wells, and they were taking layer pressures. What would you conclude if you went out and drilled a well and you found the pressure very close to virgin? Infill drill. But remember, we're working with a ratio, and I want to keep reminding you, a Qmax over G sub I, the more permeable layer divided by the Qmax over G sub I, less permeable layer. If I drill an infill well and I multiply the Q by 2 in the numerator and Q by 2 in the denominator, what have I done? They cancel. Now, infill drilling says that when I abandon out here, I'm going to have the exact same pressure in each layer as if I had 1 well, 2 wells, 3 wells, or 4 wells. Amazing, isn't it? You really have to work through this one because it just doesn't make sense that you could drill additional wells in the same reservoir and the layer pressure won't change. Now, you accelerate production. You know, you collapse the time. That's another characteristic of layered no-crossflow reservoir. Because of this type of behavior, you have real long producing times, where the early part was the high perm layer and the late part is the low perm layer. The Kansas Hugoton is projected to last for 180 years from the time that it was turned on. Oklahoma Hugoton, about 120. You look at that, say 120 years, and virgin pressure, it's obviously a case for infill drilling. It's not economical. It wasn't for them. It would have been economical had they been able to get it classed as new gas reserves at $3.50 an M, as opposed to the old gas contractor about 50 cents an M. You know, so you can see where they were coming from. And reservoir engineers had to prostitute themselves in order to try and sell it. Isn't this interesting? And it's real, okay? You know, just like we all looked at data where the P over Z, where the pressures appear to be horizontal. It's obviously bad data. It isn't. It isn't bad data. I'm trying to tell you something. This is taking the same type of approach, but now we're going to look at rate time instead of the P over Z, where we're the Qmax over G sub I ratio, and the volume ratio here we're going to use is 1:1. And for simplicity, again, it's always easier to talk about permeability contrast, but you're assuming something. The skims are equal and the pressures are equal. And this would be the rate time of the 1 millidarcy layer, and this would be the rate time of the more permeable layer. And as you can see, we were working in a region of the Qmax over G sub I ratio about 10, which would be, this is the sum of the two forecasts. You know, you get into the high B value approaching about 0.9 or 1. The permeability ratio of 3 starts approaching a B value very close to single layer. But look what happens as the ratio gets very large. You know, one of the layers becoming tombstone almost. In the old days, you'd classify it as non-reservoir rock, non-pay. Well, this is what happens. You're depleting the more permeable layer, and after it's all gone, then the other one, the low perm, kicks in here. Now we have a double depletion decline, just like a dual porosity system. Okay? Exactly the same. Remember what I tried to say the other day is you can have natural fracturing to give you the contrast in permeability that you need to get a layered no cross-flow reservoir behavior. Okay, it's not saying that a layer isn't naturally fractured, but it could be the natural fracturing that's giving you the layering behavior or the contrast that you need that you wouldn't have if it wasn't naturally fractured. Okay, you've got to have the contrast for it to start to become important. So you can still have a naturally fractured reservoir and have it layered no cross-flow. We insisted that this run be made for us when we were working with Chevron, and they were running the model, and we were helping pay the bill, that they run a no cross-flow case. And they did, and the results, they said that it's absurd. That was the end of it. Well, all we got out of it was the run. And then later they had a dual porosity forum in Colorado, and Union, I think it was presenting results that they got in modeling their offshore California Monterey reservoir, where they can get a history match was by assuming no cross-flow. And the guy from Chevron said, huh, that's what Phillips tried to tell us a couple of years ago. So, you know, we're coming from the same place. When you start knowing what to look for, everything begins to become consistent. It's not saying the reservoir is not naturally fractured, fractured at all. If it's natural fracture, it could be causing this effect. And the way to answer, like we said yesterday, is just to go out there and try and get layer pressures. And if you can't get them with RFT, maybe you can get them with Packers. But you can answer the question. Because if it is naturally fractured vertically throughout, the pressure gradient will be exactly the same. It'll just be the gradient of the fluid that's in the wellbore. And remember, you can have a more permeable fractured layer up high, and it can gravity segregate, so you can still produce a secondary gas cap with that type of scenario too. You can also have water invading with the top of the reservoir before it ever hits some of the ones internally. It's all trying to tell you the same thing. Water influx would preferentially occur in the very high permeability layer. And if it's on top, you're going to have upstructure wells watering out on you. The very first thing you would do would be to conclude you got a casing leak or something. Not necessarily. So we ran some cases to see what would happen. You know, this is he's trying to utilize models. This is the volume ratio of now 1 to 2, which is actually what we had in a red cave. In order to give us a B value of 0.9, you had to have more volume in the low perm layer than the high perm layer. So this is what it looks like. This is the more permeable layer, volumetric average pressure in a more permeable layer, like from the model. You just integrate the pressures over the entire area. And this is the volumetric average pressure of the more permeable layer. This is the volumetric average pressure of the less permeable layer. And the only thing that's a straight line is the volumetric average of the whole system. The whole system has to be a straight line. I can tell you that we tried, like in the Oklahoma Hugon, well, how long would it take if we shut in the well in Oklahoma for the pressure to build up to this value due to backflow? You know, if it takes 180 years and I'm producing almost against a zero pressure, how long do you think it's going to take if I shut the well in where the wellbore pressure keeps increasing because I'm injecting gas in the other? A lot longer than 180 years. I think it would end up, I'd take about 500, maybe 600 years for layer pressure to equalize. We took the time in the Cook Inlet Reservoir, Alaska. We have two separate reservoirs that were being commingled at the beginning. They're 1,000 feet apart, so there is no cross flow. They were at different pressures. The upper one was normally pressured, the lower one was abnormally pressured, and somewhere down the line some engineer had a great thought, is let's commingle these two wells and let one inject in the other, and it'll equalize reservoir pressure. It was physically done, and I think it might calculate it take maybe 2,000 years before it could ever equalize. You'll never get there from here. What we ended up doing was running a 72-hour shut-in and a 72-hour drawdown about once a year with the model. We simulated physically shutting in the well just like you'd run official tests, and I think we used 8 or 9 9-hour time steps or 9 8-hour time steps. And we verified with a radial model that this will give us a 72-hour drawdown and build up just like you would get analytically. So what we were trying to do was, all right, let's shut the well, and what would it look? This is what a 72-hour annual shut-in pressure would look like, the circles. Okay? That's this. And as you can see, it basically tracks that of the more permeable layer. Now, out in here where the pressure, this pressure starts getting low and this gets a little higher, you're injecting more and more gas into the high perm layer during shut-in. I can tell you in the Oklahoma Hugon, so I won't forget, because that was low-priced gas and there was a gas bubble in the United States, excess capacity, and a lot of the pipeline companies had take-or-pay contracts where they had to take or pay for gas they contracted out at $7 an MCF. And the gas coming out of this area was around maybe 50 cents or $1 an MCF. What would you do? Where would you take your gas first? Not out of here. Well, there was curtailment in the Hugoton fields. And you'd go into the model that we'd matched, and during the period of curtailment where you cut back production, there's backflow going on over a 5-year period of time, physically within the well. Here's the line pressure that we set. You see how the data comes in asymptotic to the line pressure? I think within the paper we have an example of a couple line pressure changes, and you see that this data, that this flattening is real. That you could predict it even by running a model. The other aspect is the distance from here to here. The total system P over Z and with a high perm P over Z is exactly in proportion of 2 to 1. This represents the volume in the low perm layer, the distance from here to here, and this represents the volume ratio in the low perm or the high perm layer. So the more curvature that you see in here, it's trying to tell you there's a bigger volume in the low perm layer than the high perm. You could take a pair of dividers and you can go all along this whole curve, and it's exactly, you get 2 to 1, 1 to 2, whichever way you want to describe it. Exactly. From here to here is the. You could use this, and you'll see it when we get into the Oklahoma Hugon, if I don't forget again, that the Crider and the Winfield are about at the same pressure. So if you take with the sum of those two and add them together, you'll exactly get the distance from here to the pressure in low perm layer. It's exactly in that proportion. So we have a 3-layer system, but the rule works even there. I can add those other two together. That's the other concept. If I was to go through with 100 layers and calculate the Q max over G sub I of every layer, its pore volume and its potential, whatever you want to assume the skin, all layers where the Q max over G sub I are about the same, I can lump those all as a single layer. Okay? That's how you do it. Physically. And the one that has the highest number for Q max over G sub I ratio is going to be the lowest in pressure. If you plot the P over Z's for a dozen layers, they'd be in order of the Q max over G sub I. Each one would successively, as it gets lower and lower, would go higher and higher on this curve. Okay? I'll throw out something else. You know, if I were to use the Q max over G sub I, I'll tell you now so I don't forget. Well, I'll put it in this other overhead. I'll take a break in a little bit. But the culmination, what we did in that paper was to come out with this table, which kind of relates the Q max over G sub I ratio. Again, that's the more Q max over G sub I, the more permeable layer, divided by the Q max over G sub I, the less. We got that ratio going from 1 over here to 1,000. And then we produced the volume ratio of this, the more permeable layer, divided by the less permeable layer. And if this ratio is 1, it's going to have exactly the same B value as you would have for a single layered system. When you get up to 10, you know, for this volume ratio, I'd expect the B value around 0.6 or 0.8 or 1. Notice, for me to get into the range of 1, I've got to get to a volume ratio starting to approach about 1 to 2. And so the B value is going to tell me, a very high B value tells me that I should be looking for a volume ratio of something like that. Approximate, okay? Don't have to be exact. Now, if you ever go back and read all the papers ever been written, what this is trying to tell you, the worst condition for rate time is a ratio, a permeability ratio, roughly. Let's talk about that for simplicity. A permeability ratio is 10 to 1. It gives me the worst condition with regard to rate time. If you go back and read all the pressure transient papers that have been published on layered no cross-flow reservoirs, I see what permeability ratio that they use to publish their papers to get dramatic effects from investigation of the problem. It's 10 to 1. You know, because if you move in this direction, you towards 1, it acts like a single layer system. When you move in this direction, the one layer becomes tombstone, and you end up with a double depletion decline. You know, so there was no problem. You had no problem investigating layered no cross-flow reservoirs, even for pressure transient, unless you got into this region, and that's where everybody did their work to get the most dramatic results of their study. You know, everything starts kind of tie together. And I put this on here, you know, to remind me. I hope it's on yours that you really better look at this in terms of gas ratio instead of just the volume, because the ratio of pore volumes is always equal, regardless. But the ratio of the gas in places will be different because of the differential depletion. Okay? Important to remember that. You know, like here, again, they say, well, you add in a 0.4 and a 0.4, that's how you get a 1. But you may have already skipped to the next table. We decided, all right, we did single-phase gas. Let's look at what we'd get with a single-phase liquid, where it's 0. You know, it's exponential decline. The ratio is 1, and you get up to 10. You can see, well, you got to get up to higher volume rate, but you can get up to volume ratios of about 1 to 5, and you start getting into B value of 0.6, even for single-phase liquid flow, where each one individually is exponential. You're adding two exponentials together. You know, so this, it kind of makes the point, well, that only works for gas to get that high B value. You can get pretty high on the single-phase liquid.